Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss about the mechanical properties of nanomaterial. This week we specifically focus on the different mechanical and functional properties of nanomaterial. So, last class we have already discussed the mechanical properties of metallic and ceramic nanomaterial, and today we will try to focus more on, let us say, the polymeric material, or how to improve the properties of polymer matrix by incorporating or strengthening them by some nanoparticles. Now, usually when we produce some nanocomposite by mixing a polymer matrix or along with some nanoparticle, we call it as polymer filled composite. Okay. So, this polymer filled composite could be we can use some different types of second phases, okay, with different geometry. Like we can use, let us say, nanoparticle, we can use some nanorod and nanotube. You already know about all these different geometry, what is the meaning of a nanoparticle or rod shape or tube shape, and we expect that by incorporating these type of particles or second phases, we can improve their mechanical properties. As a schematic, I show you here a stress strain plot and a unfilled composite, which basically means only matrix, a polymer is present, but there is no other second phase is present. So, the plot will give you something like this here: stress and strain, very low strength level and a large plastic strain you can achieve. Okay. However, if you incorporate a fiber inside a polymer matrix, then both the stiffness and strength. So, we are talking about stiffness, means Young's modulus, and the strength will be improved. Okay. However, we have to compromise with some plastic strain. On the other hand, in case of particulate filled composite, nanocomposite, we may expect a relatively large scatter of data of this nanoparticle filled composite. Now, the question arises, why such kind of behavior exists, let us say in case of particle filled composite, and what are the reasons? So, the major problem for composites or making such kind of composite, such means basically I am talking about nanocomposite actually. So, such a composite, we need the filler that should not agglomerate, means I want to introduce a particle to get a effective strengthening, as you know actually sigma is equal to G B by L and all this. So, here this is the length, pinning centers and so on. So, everywhere the homogeneous distribution of these second phase is very much important. However, if these particles tend to agglomerate or make an aggregate, that gives a poor property. On the other hand, there is a matrix and there is a second phase, there should be a good bonding between the matrix and the particle, which is expected. How does it really affect? We will discuss in a minute. Let us assume that I have a large particle. Here large basically means, let us say, micrometer size or much bigger than that kind of 250 micrometer or 300 micrometer size particle. So, I may have such a particle inside a matrix, and here is the particle. Now, while we put some stress into it, then due to insufficient adhesion of the particle and the matrix, okay, there will be some delamination, or let us say the interface will break, and so we will get a crack of such a size, elongated size, and the material will fail. And there is a relation between the strength of a composite which is linked with the size of a crack. So, here this is similar like a root of the crack length, which is inversely proportional with the strength. Now, if I think about a nanoparticle, so this is a very small nanoparticle is incorporated in a matrix, and if there is a delamination between the matrix and the particle, then the size of the crack is also in the range of a nanometer, right. So, we expect a higher strength of a composite in presence of a flaw, and this is somewhat very much important aspect. So, smaller the particle size and smaller the flaw size, larger the particle size, larger the flaw size. So, here strength decreases, here strength should increase actually, and higher strength can be achieved in case of nanocomposite. Now, the problem begins when we have such a particle which are not homogeneously dispersed in the matrix. Here we show you a homogeneous, relatively homogeneous dispersion of those particles. So, if particles agglomerated together and then they make a cluster form, and so these cracks whatever form around a particle will tend to join and give you a larger crack. So, here the C is quite larger. C means basically the crack length I am talking about. So, agglomerated particle will effectively increase the flaw size, and therefore, the strength will again decrease, and therefore, you may realize now that the effect of the particle size is important in ceramic. Let us say I am incorporating a ceramic particle here. So, ceramic polymer nanocomposite, but the distribution of the particle is also important. On the other hand, the adhesion between the matrix and the particle is also important. So, interface should be very strong. This is one of the very fundamental aspect of designing nanocomposite and to improve the mechanical properties. Now, we have learned that larger particles of the filler and the agglomeration, they are actually provide you a poor properties, and therefore, we need a stronger bonding between the particle matrix at the interface. Here I show you in the left hand side a stress strain plot of matrix, that is polyaramide 6. So, a pure polymer that provides you such a 80 megapascal or less than that strength, a larger strain, whereas if we filled it 17 nanometer particles, then we may get such kind of stress strain plot, whereas if we put 18 nanometer, then it will give you such a plot. Means the smaller the particle size, means second phase, the higher the strength can be achieved, okay, with compromise with some plasticity. However, these are let us say some particulate silica which has been incorporated in the matrix. Now, on the other hand, we can think about let us say where filler particle that sometimes act as a flaw, or let us say insufficient bonding, that may also happen. So, pure PMMA, that is basically polymethyl methyl acetylate, that will give you such kind of strength, whereas if you add some alumina, then both you have seen that the strength decreases and there is a little improvement in the plasticity. So, this is just a adverse situation than what we expect here, and therefore, the mechanism involved on strengthening is important. So, not all time we expect, even though we expect that the strength will increase if we incorporate nanoparticle, but both the bonding as well as the distribution of the particles are important, and there should not be any agglomeration and there should be sufficient bonding at the interface. Now, the second type of composite, that is called as a platelet filled polymer. So, here second phase is basically a platelet shaped. So, this is the ideal microstructure I have shown you, which has a nanoplatelet filled composite in a polymer matrix. Now, if we provide some stress here, then there will be some elongation, and beyond certain strain the smaller crack will appear here, okay, in between the particles or near the interface, and this is a crack you can see which has been arrested by these two particles. However, here the binding of the binding material, that is basically matrix, has failed. In case of any composite mechanics, we call, even though the whole structure appears to be rigid, but if one of the phase fail, then the composite fails. So, here there is basically a failure has occurred inside the matrix, even though which has been arrested by this two particle nearby. So, load is still continuing through this path, okay. Load is still continuing through this path, because there is a good bonding still now exists between the platelet and the matrix. That the question is whether such kind of example can you see in real life? Yes, this is a Nasser which is basically a mother of pearl. Okay. You have seen those hard shells, or our human bone, which are the very nice example of such a platelet filled composite or nanoplatelet filled composite. How? Here in our bone we have minerals platelet, which appears such a plate, this is a mineral, and we have collagen or protein which act as a matrix. So, this collagen is also present, which are the hard collagen that is also present in our bone. So, that basically gives us such a strength of the bone. And so, you understand that application or the use, or let us say the wide properties of this nanocomposite are so much important, which is also available in our body. Now, the different variation in the arrangement of such a filler particle in a nanocomposite is important. Let us say a very a common example I can show you here. This is a matrix and this is basically the filler platelet. Okay. You can see the crystalline platelet, they are agglomerated together, and these are multiple platelet actually. And so, this distance is also high, and so you do not get a very high strength, even though you expect that you have added some nanoplatelet here. But this conventional composite, the particle which consists of the stacks of layer that are distributed randomly in a matrix. But if we can somehow detach these individual plates and then distribute it in the matrix, then we can introduce effective strengthening. However, in that purpose we have to take care of this platelet. How? We can attach some other functional group which will give some repulsive force between the platelet, and it will help to distribute the platelet in a homogeneous way. So, therefore, in this composite, let us say in case of B, the layer are individualized, means we have made some defoliation. So, defoliation basically means you take out one of these platelet and distribute it randomly. Okay. So, this is the idea of defoliation. So, this is a defoliated or distributed orientation of the platelet. Now, we can further improve the situation, and a nanocomposite, let us say according to B, but here more or less equally oriented platelet we can produce and here this is the structure you can see that are very similar to the nest. So, we can introduce some effective strengthening. So, we can also call these as a platelet reinforced composite, and very similar situation we can also produce in case of a some sort of tube like composite, or let us say where nanotube are incorporated. Okay. But what is the reason of making such kind of aligned composite? Is there any benefit, or let us say randomly oriented composite, is there any benefit of it? And therefore, we need to see and discuss about some of the fundamental aspects of it. Let us say usually when we introduce some fibers, this fiber length is important, because continuous fiber is necessary for effective load bearing capacity. Here the terminology we use continuous, this continuous fiber does not mean that the physically the fiber is continuous. Here the stress profile is continuous. So, this is something like the stress profile which is continuous along the particle along the fiber here, and this is the smaller one. So, there is a very nice equation that provides us to estimate whether a particular length of a fiber will make a composite continuous fiber reinforced composite or not. In that case, we have such a equation which says that the fiber length should be greater than equal to 15 times of the fracture strength of the fiber or the plate, along with the d, which is basically the thickness of the plate, and with the interface strength. Okay. So, let us say I can give you an example of a fiberglass. So, fiberglass has some diameter of let us say 10 micrometer fiberglass. If we incorporate there and if we put this value of the strength and so on, you see that there is a 15 millimeter and things like that can be needed. Now, the same fiber length will decrease if I make this diameter of the platelet or fiber into nano level. So, if I have nano, then the length required to tell it as a continuous fiber composite or to get a continuous stress profile is less. So, I can have much shorter length of the fiber which can produce a continuous fiber reinforced composite. So, only I need to make this d in nanometer level. So, so thinner fiber is somewhat more beneficial in that case. Now, I show you such kind of a platelet field composite, and this is a nano composite where we have added some Montmorillonite. So, these are aluminosilicate available as a clay, and so you can add it in a polypropylene matrix, and one can see that these are those Montmorillonite which are distributed. However, there is a large agglomerated particle which is not beneficial for any composite, and we need to defoliate these particle and to distribute them more homogeneously. So, this is a distributed defoliated particles. You can see this is the length of 200 nanometer. So, these particle or let us say these platelet are quite widely homogeneously distributed. Now, we can also take such an example where we have some nylon 6 matrix where we have added some Montmorillonite, the same type of particle is incorporated. So, a typical nylon at room temperature will give you a stress strain plot like this. Okay. However, if we increase a little bit temperature of 350 K, then it will give us a little poor property in terms of strength, because we have raised the temperature of the test temperature. However, if we add such kind of silicate or Montmorillonite, then you see the both the stiffness and strength has increased with of nylon 6, and if we further raise the temperature, then it will also provide some plastic strain and so on with a reduced E modulus. And therefore, This is a very interesting feature, that if we have such kind of defoliated, then both the strength and the Young modulus of the composite is higher than the pure polymer. So, advantage of such kind of platelet filled polymer composite, nano composite are beneficial. Now, is there any other application of those composite? Yes, in automotive or aerospace industries we use them a lot. However, there are some other functional properties are required, not only the strength. However, if these material are highly flammable, then also there is no use. However, we can further improve the flammability property by incorporating some nanoplatelet. How it is? So, when we apply some heat, then there will be a heat release from the composite. Okay. So, let us take an example. Let us say I have heated a nylon 6 and with some without some nanoplatelet or with some nanoplatelet. So, this is a pure nylon 6 which is represented with a red color. So, the red color here we have heated it and then we are observing the heat release. Okay. With time, you see that the heat is released and so on, the release rate is very high and then it become basically cool down. Okay. Now, if we add some platelet, that nanoplatelet of 5 weight% silicate, then you see that the heat release rate is relatively low. Okay. And it occur on a large temperature, a large time range. So, the releasing rate is low and the effect is very simple. The effect that the maximum flame temperature, that also can be reduced. So, this is with time, the pure nylon, the maximum flame temperature increases, whereas in case of nylon silicate it is decreasing. Okay. And such a decrease is linked with both the property that the heat release rate is less and the flammability is also less. So, we can use such nano composite for automotive or aerospace industry, where there is a large heating of the composite and it has to release the heat. Now, the third type of nano composites are the carbon nanotube and graphene based composite. Usually, since these nanotube or let us say a very small nanoscale hollow tube that provides a very large Young's modulus of in the range of 0.64 to 1 terapascal, and the carbon nanotube also provide a very high strength of 30 gigapascal. So, this is like 60 or 100 times higher strength than any conventional metals alloys. This is a excessive strength that can be achieved. Also, in case of graphene, it is something like 130 gigapascal. So, such a high strength material we can use to increase the stiffness of a composite as well as the strength of a composite can be tuned or manipulated. So, you can see here a strand that is consisting of single and double wall nanotube. So, the nanotube are not directly straight, it is also some of these such kind of shapes you can see actually. So, this is a large strand of let us say 2 to 5 micrometer, and once we incorporate them in a composite, let us say that is a polypropylene matrix with a single wall nanotube. So, SWNT stands for the single wall nanotube. So, this is a matrix without any composite reinforcement, whereas we keep on increasing 1%, 2%, 3%, 4% and 5%, and both the stiffness and the strength are improving. So, the use of a single wall nanotube which can dramatically improve the Young's modulus and the strength of a polymer matrix to a very large extent. Very similar example we can get actually, that that a stress strain plot of a composite fiber, where we use some polyvinyl alcohol at the surface. So, here we take a single wall nanotube and we put some polyvinyl alcohol at the surface, okay, at single nano fiber, that is nanotube fiber, that is under the straining. Okay. So, in a microscopic scale we can assume that this is a nanotube and we put some polyvinyl alcohol on the surface and then we are straining it. So, you get such a stress strain plot where the stress level can be 0.8 gigapascal, okay, which is quite high. So, the tensile test specimen that was prepared, let us say 50 micrometer, and with 60% of the nanotubes are there. So, we can use that material and compared with the spider silk, and so we can produce such kind of high strength material. Or let us say we can also use some graphene oxide and polymeride film, where we use some 1% or 3% of those graphene oxide, and from a unfilled polymer which increases both the Young's modulus and the strength, it is also very much example is very clear. So, overall what we can see that there is a large opportunities to use these nano particle or nano fiber, nanotube, or let us say nanoplatelet, which even present in our bone can be utilized to a very large extent. So, therefore, if we look at a very common Ashby type of plot, where we have the yield strength by the Young's modulus, and so this is let us say the level of the ideal strength of the material, that is G by 10 and so on. So, in case of metal or let us say polymer or ceramic, the zirconia, alumina, glass, they all lying here, and using this kind of nano multilayer or amorphous material, we are almost reaching very close to the ideal strength of the material, okay, than the conventional material. So, these are like titanium alloys, brass, mild steel, aluminum alloys, copper, lead and so on. So, their strength level is lying here. So, both the polymer matrix that can be improved by using some nano particle or nano rods. So, we can reach very close to the ideal value. So, these values are almost like the about a 1/3 of the factor of the ideal. However, we have no chance to go beyond that, that is a theoretical limit. So, using this different type of nanomaterial, the mechanical properties could be improved to a great extent, and we can always can reach close to the theoretical limit of the strength of the materials. With this, we complete the mechanical properties of nanomaterials discussion, and we will discuss the other functional properties in the next classes. Thank you very much.